Yes, so today's title of today's lecture is silence please, multiple state machine implementation, and we will also talk about how to determine the clock period of a state machine. So very briefly, first I will review what we discussed in the last class. So these are the steps involved in state machine synthesis using counters. So we start from a state machine, we encode the states, we decide what is the binary pattern that's going to, binary string which is going to represent the state. Here of course we have choice of encodings. Once we have decided that, we also choose a counter with appropriate control inputs to implement the state register. Here we said the counter could have inputs like load, enable, even up down, output enable also, clear. So we have to choose a counter which has the appropriate set of control inputs. Thirdly, we use the counter functionality table to arrive at the specification of the combination logic. See, once you have your state transition diagram and once you have encoded the states, you know that for the present state encoding and the present input, what are the next state outputs. But this, if you are using a counter, then instead of the next state you have to generate the control inputs for the counter, whether you want to have an enable or whether you want to have a load or clear or what. So you write your table now in terms of these control inputs. Then we synthesize the combination logic both for generating these control inputs as well as for generating the output. So these are the 4 steps involved in synthesizing a state machine using counters. There are large number of applications of such sequential machines or state machines, and we will also see some examples today. The type of applications we already talked of pattern matching. We talked of overlap pattern matching, that is the pattern that we are looking for, one occurrence of a pattern can overlap with the next occurrence of the pattern. Past part of the pattern could be common to both. So that's called overlap pattern matching. We could be looking for patterns which are non-overlapped. The two patterns are completely distinct, they don't share any bit with each other. We can have blocked pattern matching, where we are looking for a certain pattern in a block of bits. It could be block of 16 bits, block of 256 bits and so on. It could be non-blocked pattern matching, like what we had before was non-blocked. And if you look at these two, and these two are orthogonal to each other in the sense we could have overlap blocked, overlap non-blocked and so on and so forth. We could have sequential decoding. We can design controllers. Controllers are in general machines which are generate control signals, set of control signals in a certain sequence which are given by the state machine. We could have memory based circuits. These are very broad classification. We will see later on design of more specific controllers. We will also talk of alternatives to the type of design we are doing as we go, and we will also talk in some detail about how do we design circuits with memories. But today we will first talk about how do we design systems, or let us say we will consider actually 2 examples of systems where we need to have not just one state machine but more than one state machine. So we are talking of interacting state machines, and we will start from an example. You will see that the methodology that we are following is a little ad hoc. It does depend upon some experience, but this particular thing can be extracted out easily from the specification of the problem, whatever we are doing, and it should be clear that this is one obvious way of partitioning the system into multiple state machines. So now we are talking of here a blocking, search for a pattern P, so some pattern 1101. First we have to receive 1, then 1, the next 0, then 1, within blocks of 256 bits. The pattern should not cross block boundaries. Overlap is permitted, but blocking is also there, in the sense that if I am looking for, so if I am considering bits, this is let us say the first 0th bit that is received and 255. So this is 256 bits. So I cannot have a pattern which is 1101. I cannot have a pattern like this. So this is not an acceptable pattern. The whole pattern has to fall within the block boundaries. So that is the problem that we are planning to design, synthesize. And so I can do it in this manner. I can design two state machines, M1 and M2. I am talking of not designing now one state machine, two state machines. One is a modulo 256 counter, something which is just counting 0 to 255, and M2 is a pattern recognizer. I can go ahead and design this M2 in an exactly the same manner as I have designed previously. But of course, we will see that because now both these two things have to work together, some modifications would require to be done. The way I look at it is, each time I start a new block, this is a new block that is I am starting, each time I start a new block, I should be initializing my M2 state machine. That is what is really required. What is required is M1 is just going modulo 256, and each time I should be able to initialize. So, it does not matter even if I have got this 1 1, I should still go to the initial state rather than continue with the transitions which are required for the pattern. So, this is basically this splitting into two machines is, you can say that is ad hoc in the sense that I have to do this. I do not have a methodology really to do this. So, this from this problem specification I can come up with this. So, what happens then if I do this? So, I have actually two state machines here. So, one state machine is nothing but a modulo 256, a free running counter. What I say is a free running counter is just running S0, S1 for every clock it makes, performs a transition, goes to S255 and comes back. So, this is my one machine which is M1, and I have another machine M2 which is a overlapped pattern recognizer. Overlap pattern recognizer, essentially I receive an input. So, because I am looking for 1101, this is the pattern I am looking for. So, if I get 1101, I will return over here because with an output of 1. Anything else I will have to go to somewhere else. If I first receive a 0, I will get stuck in state A itself. If I receive a 0 from here, I will return to state A. If I receive a 1 from here, I will come back. If I receive a 0 from here, I will come back. So, of course, I can see that how much of overlap happens for a wrong input, and I can appropriately return to the state that gives the wrong input. Now, this is a state diagram for M2, and now what I really need to do is I need to design this, let us say, complex or multiple state machine. What this is a combination of both M1 and M2, because what I now need to impose is this fact that I do not permit my pattern to cross this block boundaries, where the block definition is 256 bits. So, the diagram is now going to look like this, a machine which has both M1 and M2. Of course, so there is something from M1 machine which is counting 0 to 255, some information is going to go from M1 to M2, and of course M2 is the machine which receives this X as the input and generates this Y as the output. Output Y is nothing but the case when the pattern matching occurs. Now if I translate this into my problem, that is M1 I have to detect the block boundaries. So, this will mean that I need to modify my state diagrams little bit, and the modifications are like this. First, let me see the modification that occurs in M1. This M1 is again a free running counter, except that what I need from this counter is one output I need. The output that I need from this counter is essentially to say that I am going from state, I am in transiting in the last transition corresponds to an output. I will reach this in the 256th clock, and I will reach again in the 256th clock. So, after I have reached here, so in this portion I need an output 1, which means that I am in the going to perform my last transition. And this particular output is the one which is going to be fed as an input to, if you remember, see this, after all there is an output going from here and which is going to be an input to M2. And this particular input is now shown over here. So now I have modified this. I will explain this diagram in a little bit more detail, but basically I have modified it to take two inputs and not just one input. One input was anyway there before. The two input, the second input is, if you consider M2, it has now two inputs, one coming from the external input and another is input coming from M1. There are two inputs. And the role of this input is primarily in terms of initialization. What it should be able to do is it should be able to initialize this state machine back to, because the block boundary is going to begin, so I should come back. This does create some complications over here in terms of the state diagram that you need to realize. So now if you consider two inputs, there are two bits that are coming as inputs, so there are basically four possible transitions at each stage. Each state. Previously I had only two possible transitions in each state, so I had four possible, but some of these transitions are actually going to the same state and also they are generating the same output, but that is not true for all of them. Let us look at first state A. Out of the four possible transitions, three of them keep it in the same state. What are the three of them? If I actually receive a 0 as an input, actually here the first input is coming from M1, so this is M1 output is the first input, okay, and X is the second input, the two inputs that I am showing over here. So if I get a 1, that is if I am in initial state and already the block is going to end, then I will remain in A initial state irrespective of what my input is going to be, because I had to restart my pattern matching. So I will be 1x is the input for this. So 1x actually corresponds to two input patterns, it corresponds to 1 0 and 1 1. If I get 0 0, of course, though I am not at the beginning of the block, but I am getting a 0, and because after all previously also if you looked at the previous state diagram, there will be no change. So if you look at this previous state diagram which considered only one input, what will it correspond to? This corresponds to the first input, the output of M1 being 0, this particular diagram will remain the same. After all, if it is, we are not at the beginning of going to begin a block, the pattern matching is going to go on as before. So this particular diagram is exactly, so now all these two transitions have to be preserved at each state, but the next two other two transitions which correspond to beginning of the block, or basically because we are doing everything synchronous, we are talking of end of the block. I will clarify this again in the implementation part. So it is fairly straightforward. So if I go from here, if I look at B, B has again now this particular transition which corresponds to 0 1, corresponds to the previous transition of the block being matching being progressing, 1 1, the matching being progressing, but in case I receive 1, I come back to A. 1x is going to bring me back to A, 0 0 was also bringing me back to A, so now the condition is 0 0, comma 1x. When I write comma, is basically here it implies OR. Condition is either 0 0 or 1x is going to bring me. These commas, separation of these are the various input conditions for this transition, and they essentially correspond to OR of these conditions. Now let us look at B. So B again we go to 0 1. Now let us look at C. C, if I get a 0 0, I will go to D. The pattern is matching is progressing. But if I get a 0 1, I will go to B, because after all 1 1 pattern will keep it here. But if I get a 1x, I will come back to 0. So I proceed to D. D is a little more peculiar here. I have one transition which is correspond to the previous one, 0 1 1. I will go back to B. But now what happens is, if I get a 0 input, doesn't matter whether I get a 0 or 1 here, I will come back over here with a 0 output. But if I am in this particular state and I get the last pattern, but I also get the fact that block is going to end, now I should not return to B. Like previously 0 1 would have returning to B, but 1 1 is going to return back to A with the output of 1. So, but if you consider this particular transition now corresponds to two things. If there is a cross 0 is the input, I have 0 output, 1 1 is the input, I have 1 output. Okay, so this is, so once I have drawn this state diagram, rest of the synthesis process is very straightforward. I will use exactly the same techniques as I used before. I will encode the states and so on and so forth. But the important thing is I have been able to solve the problem by partitioning it. If you try to apply the whole methodology to the initial specification, it will become extremely complex. We will see that why it becomes so complex. So this partitioning is very critical to solving such problems. So we have this M1. M1 now is nothing but a 8-bit counter, which is a 8-bit free running counter. It generates an output, and this particular output, now I am doing a little more, let us say, intelligent synthesis or using some techniques that we have learnt. So now I know from this particular state diagram that each time I get a 1, I go to initial state, irrespective of which state I am in, because the next state is again going to be A. So I can, what I can do is, I can part of this, I can synthesize using combination logic, and this particular fact that basically I am going to be going to state A, I am synthesizing using the clear input. If for rest of your synthesis also you need to use this clear input again, you can OR that. You can generate, if there are other conditions also you like to clear. For example, there are situations you are coming back to, even with for example a 0 you are coming back over here. So you want to implement this particular edge also using a clear input of the counter. You can take this condition and OR it with the condition that is there for this. But what this does is, this helps me to simplify the problem considerably, and not only that, what this helps me to do is, I could actually almost use the same M2 I had before. If you look at this,
sir,
yeah.
I have a small doubt. When the counter is registering the transition from 255th state to the 0th state, that means already 256 bits have been read, or is it that 255 bits have been read?
Can you just wait for a minute? I will answer this question because I am going to show the timing which will clarify this. If it doesn't, then you repeat this question. We will come to that. So this particular, so one thing is, of course, as I said, you can use the methodology that we have discussed and synthesize this machine. Okay, completely starting from the basics. You can write the input output states and write the combination logic. But you can also use the fact that because what we really need from this problem, it's clear that what we need is, I want to go to the initial state for M2. So I can use the design of M2 that I did before with one additional change. Of course, if I are using some clear inputs there, I can OR this clear input with the new input that is coming from M2, and this will also achieve the same result as before. So these are some of the things, you can considerably sometimes simplify the problem if you understand the problem and understand the realization. The fact that now you have to know a little bit about the hardware that is going to be implementing this, because the brute force method of implementing the 2-bit state diagram may lead to lot more logic, lot more gates than the fact that you actually use this information that this clear can be useful. So I have an 8-bit free running counter for implementing M1, and I have counter with synchronous clear, and now it's very important that this clear actually dominates, in the sense that if I have, let's say, implementing it using load, or I am using enable for going to the next state, This clear has to dominate in the sense that it should override the others. When the clear comes from this, it has to clear. So that also we discussed last time, that from the table one can actually figure out what dominates and what doesn't. Now perhaps this will clarify the question that was raised in terms of the timing. If you look at the M1 machine, which is actually generating the output. So I have this particular clock, okay. So this particular clock, and this is a free running counter, so it's going to some S253 state, S254 state, S255, S0, S1. It will keep on going like this. This is not something which is going to stop. Of course, initially it should get synchronized with the first bit that is coming in. Okay, that part is still there, but we are, let's say, we are assuming that at power on everything is synchronized. So now this particular state transition, follows this. It's all rising edge triggered, and the state change actually follows this. After this edge comes, after a small delay, which delay corresponds to the time that the counter takes, and this we again have discussed various types of counters last time, the ripple counter and the synchronous counter. So assume that these are all synchronous counters, and so after a small delay the outputs will stabilize and we will get a state corresponding to whatever. Now, because if you consider this particular diagram which we had for this particular state machine, this doesn't have any input. Okay, so the reason I am using a dash is I am just distinguishing between don't care and dash. Okay, don't care implies that there is an input, I don't care whether it is 0 or 1. Dash here I am implying that there is really no input. Okay, because, but if I just write 1, it will look like the Moore machine, okay, with only the output specified. That's why I specified a dash. And so there is no input here, it's just going through and it's generating an output. And this particular output is a mod 256. Okay, so no, okay, this output is the output which is the clear. Let me write the clear input to the next machine. And now it has to be a synchronous clear, because what I really need is the other machine is actually getting the same clock. This clear will be a little bit more delayed with respect to this state. Okay, because whatever mechanism you generate this clear, you may be decoding this state. 255 has to be decoded. You can use an 8-bit AND gate to decode this state. So once you decode it, there will be a small delay of the decoder, whichever you are using to decode this state to generate the clear. And if you now look at the timing, it is at this clock edge that I will go to the initial state on the M2 machine, because it is going to get a clear and it is a synchronous clear. If I don't use a synchronous clear as we have considered before, I would have to generate not with 255, but I have to generate with S0, because it has to do an asynchronous clear, it will immediately clear. But that will obviously mean that it will go to some other state for momentarily and then come back to state 0, depending on where the transition is. So in this case it will actually end up as we are doing a synchronous clear with clear dominating over all the other inputs. The other inputs could be load or enable inputs, and so it actually will reach. So as far as the next, if you consider the M1, doesn't matter where it is, I know what state this state is going to be A, irrespective of what it is. And this corresponds to every 256th clock edge. It is a 256th clock edge, okay, so that you will, and that is the 256th bit, and I am assuming that the inputs are coming synchronous to this clock. That is, every clock a new bit is going to come, and I am looking for blocks of 256 bits. Does this clarify the question you have? Okay, so let's just to reinforce this. So it's not just that we always have to build two. There are also more complex situations, because typically when you do your sequential machine design, you will find that, especially, it's not that the whole problem nicely breaks down into one state machine. We have to talk in terms of multiple state machines. Okay, before I start this, let me tell you what is the actual complexity of this particular. If you consider this overall as a one single state machine, let us say if I don't really have to design it in this manner, the number of states that this particular machine, actually if you look at it, the machine can arbitrarily be in any one state of this and one state of this, if you consider M1, M2 together. So actually it has 256 into 4 states. If you consider this as a single state machine, and so that's 1024 states, and obviously designing a machine with, if you really want to break it down into individual states, it is going to be extremely complex. And the design itself may be turn out to be extremely complex. So one needs to do this partition, and which part of it, okay, this pattern matching part we can use the same methodology, and here you can recognize that it is a free running counter. So we see that similar situations, another one example which illustrates what we are trying to say. The problem is a little different over here. We are talking again of a bit stream. I am getting one bit at a time, but these bits now actually correspond to ASCII codes, character codes, 8-bit ASCII code, that's what is there. And what I am looking for is, let's say I am counting the number of some character, in this case at I have taken. Let us just say, for example, it just consists of a string of bits, and I am trying to find out how many email addresses are there, and let's say all email addresses, there is the only place where you have an at, for example. So I have to count the number of characters, and these are all, the data is actually blocked, and the data has 256 8-bit characters. So that's the length of each block. Each block consists of 256 8-bit characters, and I am planning to count, or my intent is to count how many at characters are there. So there is some character code, ASCII character code for this, and I can do a pattern match for that particular character. But here there are two things here. Now there are two synchronizations that are required. There are two blocks. One is the character block. You start from, look from 0 to 7 bits, then 8 to 15, then 16 to 23. So you have to go in those. So the character is not going to spread over. So in terms of this blocking, it's not going to spread over half number of bits here and half number of bits there. So it is actually, so there are two levels of blocking, and then there are 256 such characters. And I am interested in, there is an at character coming here, there is an at character coming here. I need to count how many such at characters are there in a block of 256 characters. So if you look at this, of course one can design it with 3 machines, and one can design it with 4 machines. So I am doing it with 3, one can also, I will also indicate that. One is a pattern recognizer for at character, because this is just a sequence of ones and zeros, and I look at the ASCII code for at, and I can do a pattern recognizer for that. An 8-bit counter for counting 256 characters. I need to count 256 to get the block, and I need 256 characters. Another machine, M3 8-bit counter for counting number of ats. So I need to count how many at characters are there, and so I need another counter for doing that. What is important is, okay, you can say that you have to have very clean interfaces between them, and those interfaces are the ones that you should realize that make the design simple and realizable. So here I am showing you a design of this. So what is the specific, so I consider, okay, before that let me tell you, when I am looking for an at character, so this is, I don't want to count the 8 bits separately. There is also a mechanism that you can have another machine to count 8 bits. But in this case, I start from some state, let us say A, and there will be a sequence of states A, B, C, D, E, F, G, H. Up to state H, which corresponds to the sequence of bits that you really require for detecting 8 characters. But what happens is, if let us say you don't get the proper bit, you want a 0 and you get a 1 over here, then you go to another sequence. If you don't get this, you will go to this particular state. ij some. So starting from this, so when I come back to this and come back over here, or finally I come back from this particular state, I would have got exactly 8 clock pulses to get back. Okay, so that's important. So because these 8 bits are going to correspond to because after 8 clock pulses I should again come back to this and I can again look for this. So in this case, when I am doing a design like this, so the pattern for looking for 8 bits, I don't need a separate counter for that. These particular edges I can associate an output, some output 1 output can come from here, which indicates that I have got 8 bits. So I don't need another 8 bit counter for doing that, because this particular state machine itself can give me the blocking, the first blocking, the 8 bit blocking. Because so this is, if I come back in this particular fashion, then I actually get a correct character. And if you don't get back in this, if I come back at any place, there is no path to get back to this, because this is the exact sequence, whichever is the bit pattern that I am looking for, I will follow this and I will get back. So in this manner I can actually avoid having a separate counter for So what is the specification of M1? So now I have 3 machines, M1, M2 and M3. Specification for M1 is I am generating 2 outputs, Y1 and Y2. Y1 is 1 if the last 8 bits that I have received is the bits corresponding to whatever character, add character, and T mod 8 is equal to 7, that is I am in the last, because I am looking at xt, xt minus 1, xt minus 7. So time wise I am actually in the 8th bit. The T is nothing but 7. So T mod 8 is 7, means basically I am at the end of it. So then my output is 1, which in this particular state diagram the output will come from. So I will have 2 outputs here. One output corresponds to the correct bit pattern that I am receiving, and this output corresponds to the wrong bit pattern that I have received. So I will get this output Y1. Otherwise, of course, it is 0, that I have not written over here. 1 if this corresponds to add pattern, and otherwise it is 0. And this goes as an enable to the counter, which is going to count how many times you have received add. So primarily you are generating, you can assume that each time you get this character, you are going to generate a pulse here. But this pulse is of enough width so that a clock actually passes through, and the rising edge of the clock I am going to count with this M3 counter. Because this particular counter is going to count how many times the character has been received. But this particular thing has to be actually initialized, because we are looking at blocks of 256 characters. So each time I reach 256, it needs to be initialized. And so this particular part I can do it by using the, each time I reach at the last state, these 2 states. So each time I receive this, so I generate this particular one, which is going to count, give an input to M2, and M2 is enabled and M2 is going to count, the same clock is going to count, and when I reach S255, like the previous case, on this counter I will clear this. And so, and this particular counter of course gives the output, and you need to have to store the output. You can store it with this in some other register or some other place, because if you have to keep the count stored, because the count is going to get reinitialized and the same counter is going to be used each time to count in the next block of 256 characters how many at symbols are there. So what you can see that it's a fairly complex state machine. If you really look in terms of a single state machine, so you have this a pattern matcher here which is going to look for this. There is a one which is going to count from 0 to 255, and this is the one which is going to count again. I can count up to 256, 0 to 255. Okay, so that's a possibility, but if you are looking at the problem and if you actually break it down, so the design is not difficult. The design is fairly simple. in terms of, if you consider in terms of multiple state machines. So the point is, many times when you get a complex design, the important thing is in terms of timing, you have to be very clear about at which clock edge what is happening. Okay, so these control signals are going to imply that at the same clock edge, when you reach the 8th bit, this is going to, when you are going, so this is going to get incremented. So this is counting basically number of bytes received, this is counting number of add characters received, and you can break down the problem and implement it using multiple state machines. So when you actually look at any type of a design, you might have to look in terms of not designing just one state machine, but designing more than one state machine with very clean interfaces. You should have a very clean specification of the interfaces and not do the design arbitrarily, because this is, the partitioning may be more by experience and ad hoc, but the interfaces has to be very clean. Like what are the inputs that are coming from here and what are the outputs coming from here and going to the other block. So in this case you have M1, M2, M3 all are interacting in some manner, but both the problems that I described, there are no sort of feedback, there is like nothing was going back from here to here, there is a clean flow. Okay, feedbacks make things complicated, but even that is possible to design machines using that. So this was one thing that I want to discuss. The second part is deciding on the clock period. So we will spend some time talking about how do we actually decide on the clock period for a state machine. So Mealy, I am taking a Mealy model, one can do this for the Moore model, it is very similar, there are only some few changes from here to here in terms of the delays. So I have two parts of it, and I have to look at the specification of both parts to be arrive at the clock period. So basically what it means is, once I have made my design, can I say at what clock frequency I will operate it? Of course, the problem could also be specified differently. You could say that to do a design which should work at 10 megahertz. So I am not immediately looking into that problem, I will give you some hints on how to go about it, but basically here I am looking at the reverse problem. I made the design, and can I analyze and say that till what frequency it will work, what is the maximum frequency this particular design will work. So I have the delays that are associated with the combination logic, we will talk about those delays. I have some delays associated with this flip-flop. Apart from the basic delays, which are the propagation delays, the propagation delays are the delays which after the input changes, outputs take some time to stabilize. Those are the propagation delays. When the flip-flop is there, you also have two more delays which are associated with, or two more timing specifications which are associated with the input. If we are talking of a rising edge triggered flip-flop, this particular clock is being applied here and it is rising edge triggered. For this flip-flop to work properly, what it means is to each time to be able to recognize the input should stabilize certain period of time before the clock edge comes. And this particular timing is called the setup time. Input should not change in the setup time before this clock edge. Any input changes that should occur before. The implication of this is if the input actually changes, the setup time, let us say maybe 5 nanoseconds. For a particular flip-flop you may have a setup time say 5 nanoseconds. The implication is if it changes not, and this particular clock comes at, let us say 20 nanoseconds, this is coming at, after 15 nanoseconds the input should not change. That is what the implication is. If it actually changes, what it means is we will not be able to ensure that the change will be made visible in this clock or in the next clock. And this is indeterministic, this is not something which can be, it may happen that this change is registered, it may happen that the change is not registered. So it is a very error prone situation. So one would like that the input actually does not change for setup time before the clock. Similarly, there is also a hold time, typically much smaller than the setup time, and in some flip-flops it may even be 0. But this hold time essentially implies that for a certain period of time after the clock edge comes, input should still not change. See, basically if you look at it, all these digital phenomena is only a simplification of the analog processes that are going on in the flip-flops. All circuits, all real life is essentially analog, they are not digital. There are capacitors, there are resistances, they are charging. So it does take some time for the charging to take place when it is going from 0 to 1, or it does take some time for the discharging to happen if it is going from 1 to 0. We would like, of course, our flip-flops to have very little setup time, we would like our flip-flops to have very little hold time, but that all depends on how the circuit is designed. So hold time is a period for which the input should not change after the clock has edge comes. Typically, of course, when you talk of edge it also is never, it is sharp only in the time scale you see. If you actually keep on expanding, every edge will look like this. Everything is slanted. So all these timings are with reference to what's called a threshold at which the transition 0 to 1 is recognized. And all these thresholds are also actually device to device dependent. Typically there is a nominal threshold value for which the design is done, but it cannot be ensured that exactly, if you say the threshold is 3.2 volts, it doesn't mean that all devices will exactly have 3.2 volts. There will be some variation. But anyway, we don't have to get into those complexities in this course. But there is a specification of a setup time and a hold time which comes with the flip-flop. And those times, of course, is just an array of flip-flops, so those same thing is valid for all the flip-flops. We consider that the state register is homogeneous. It consists of all the same type of flip-flops and all these inputs are. If we talk of the control inputs to a counter, they are also like inputs. If you talk of an enable input, the load input, the clear input, they are also like inputs and they also have similar specification of setup time and hold time. When you talk of synchronous designs, when you talk of non-synchronous control inputs, then there will be a specification of minimum width. A clear to be effective as a clear, to clear the counter, it will require that it should have some width. It cannot be a spike of, let us say 0.1 nanosecond spike will not be able to clear the counters. There will be a specification of what is the minimum width of this. This for asynchronous inputs. For synchronous inputs, we will have the specification of setup and hold. So once we know all these details, now I talk in terms of the clock period. So here I specify all the timings which are important to us. The timings that are important to us are critical path delay, XPS, X and PS are the inputs, and what it means is critical path delay XPS to Y. From all the possible inputs that I have, what is the maximum delay to Y? And that is I am specifying as TO. That's TO. The maximum delay from any of the inputs to output. So if you consider all the possible paths and find the path which is the maximum length path, that is. Similarly, TNS is the critical path delay from all the inputs to the next state. So if you consider all the inputs, consider all the next state itself may not be 1 bit. Similarly, this may also not be 1 bit. So I have to consider all possible outputs. I have to consider here all possible next states. And TNS is the delay. TD is the delay of the shift register. SR delay. T setup is the setup time of the shift register. TH is the hold time of the shift register. Hold time actually does not come directly into this picture. If the hold time is very large, it comes in some other form, but typically the hold time is much smaller, so it doesn't contribute to this. But it does contribute to the fact that you have to design your input in such a manner that it follows that hold time logic. Now when it comes to the clock, I have two things, two expressions over here. Let me explain both the expressions. One expression is, after a clock pulse comes, let us say I am talking of this particular clock pulse. After TD time delay, the present state will appear. This present state will appear after TD time delay. After TNS time delay, after TNS time delay, this next state will appear over here because that's the critical path in the worst case. And all this should arrive here T setup time before, because so that in the next clock edge I am able to get this next state becomes the present state. So after going through this, I should be able to arrive here, setup time before the setup time of the shift register, and that's why this TD plus TNS plus T setup time, TD plus TNS plus T setup time, this factor comes from this. So my clock period should not be smaller than this. I should be able to complete this loop and be able to register. Now as far as this particular expression is concerned, this comes from the fact that after the clock comes, after TD of course I get my present state, and my output will take another TO time. Now of course you can argue out that why do I need the output to come before the next clock. Actually there are some situations where this condition may not be applicable, but most of the time I do want that this output which corresponds to this particular state, it's a milli model, okay, has to come in the same clock period. It should not come after this clock, because I am actually being associating with this particular state. So I am associating with the state that the machine has reached in this clock period, whatever is the state. So I should get this output before the next state. That's one thing. Second, let us say if you permit this TO to come after, let's say I don't impose a condition that this clock should be less than this, clock period should be more than this TO, and TO gets in the next clock. It is not that, please remember, TO is a critical path. It doesn't mean that the output will always come after TO. Output can sometimes come very immediately, because that all depends upon which paths are getting activated within the combination logic. It will become very confusing to look at the output, because sometimes the output will come with the next clock for this particular clock, sometimes the output will come in the same clock. And most of the time what happens is that you take the output and you generally latch it with another register. There is a very common usage that happens, and if you try to do that, then again this problem will be there, that each time when you are latching the output you do not know whether it corresponds to this particular output or next. So some outputs may just be missed because the last output has come and the next output has also immediately come before this next clock. So because of all these reasons, typically any design, let's say reasonable design tries to impose this condition that output should also be associated in the same clock period. And so TD plus TO is one expression, TD plus TNS plus T setup is another expression, and any clock period that you have should be more than the maximum of these two.
So shouldn't TH be added to both those expressions as well?
No, TH is not required. TH is actually overlaps. TH is more a condition on the input. TH overlaps with TD. Typically TH is much less than TD typically. So TH you have to keep the input hold, because after all the delays, what you really need is this particular input should be stable longer after the edge has come. But after all, if the delay is going to occur, then it is not going to change, even you are not going to go out of the shift register, so the previous input will be stable. So it actually overlaps with the delay time of the flip-flop. So TH need not be added, except for the fact that let's say you are in a very peculiar situation where TH is very large, which is not the case. Then you have to bother about that situation, but typically that's not the case. So, but what we have shown here is a very powerful thing, in the sense that this is something which is universally applicable for any type of asynchronous design. What you do is, if you have multiple modules, doesn't matter, the same thing is applicable, except that you have to find all such loops. I have found one loop. You may have 10 such loops in your design. If you have 5 state machines, each 5 state machine will generate a loop like this. You write the expression for each one of them and take the maximum of all such expressions. So we will not go and talk about how to compute clock period in multiple modules. It doesn't matter any number of modules you have. You just keep on computing for, and what is variable here? Typically if you are using the same type of flip-flops, nothing else is going to vary except TNS. This will vary because this is a critical path situation. This will vary because depending upon the logic that you use for generating the output for each of the state machines. So you just calculate this, take all such loops going from clock to clock, because there is a loop because I start from one clock and I should arrive before the next clock. So take all such loops and take the maximum of it, and that is the minimum clock period. You can use, of course, larger than that you can use for designing your circuit. And if this does not meet your specification, sometimes your specification you need a circuit which should work at 10 megahertz, let us say that is what you are told, then you have to design your TO and TNS to be able to meet the delays. That is a different problem altogether. That is, given a time period, design a combination logic which will meet the time. Okay, thank you.